At first, zero field NMR was done actually with polarization in high field, shuttling the sample into zero field for evolution, and then shuttling it back into the high field for detection. But later on, Alex Pines joined forces with the SQUID superconducting quantum interferometer device pioneer John Clark. And after that, it was no longer necessary to at least do the detection in high field, because you could do it just there in the zero field. And they have made a very, very good start in here. And then sometime later, Alex called me on the phone. We actually knew each other in a non-scientific way, because our kids went to the same class at school. But he called me up at the University of California at Berkeley, where he is in the chemistry department. I'm in the physics department, and he said, "Come over, let's talk some physics." And I came over, and Alex said, "We should use atomic magnetometers that you are developing to study NMR." And I was surprised by that, but we started doing this, and I'll tell you what happened. So my plan today is to tell you, I guess, what is zero field NMR and why one may have an idea to do this. I will tell you about NMR experiment, the full NMR experiment without magnets. This has already been quite a few years since this has been done, but I'll go over this to give you a flavor of how this works. Then I will emphasize the role of hyperpolarization in ZULF NMR. And just to open my cards here, I want to say that in normal high field NMR, you can do a lot without hyperpolarization, okay? And if you do have hyperpolarization, that's very nice. Your signals are becoming large. But in some way, in many cases, hyperpolarization is a luxury. But for us, it's actually a necessity, because you can't get any thermal polarization at zero field, okay? Then I will maybe say a few words about how we use this regime for fundamental physics by giving a couple of examples. And then I will tell you what these fundamental physics needs are, okay? Good. And the answer, again, see, I'm asking a question, giving the answer right away. The answer is we need a bucket of polarized spins, as nicely illustrated by the AI here. All right. So if you like to read German, we wrote a popular article that came out a few months ago in Physik in unserer Zeit. And I have lifted this picture from our article there, which was actually originally appearing and still is on the ZULF NMR blog. And what you see here is the high field NMR cartoon on top and the zero field NMR at the bottom. And you know, like many things in life, NMR consists of three stages, okay, three essential stages. And this is polarization, encoding, and detection. And you can recognize these stages in other fields of physics, sometimes with slightly different names. For example, in atomic magnetometry, we use polarization, precession, and readout. Or detection. And in quantum computer, that is initialization, operation, and also readout. And so this is like a typical situation for many different kinds of experiments. So the basic idea of zero field NMR is that we look at how magnetic field, high magnetic field, is used in each of these stages of regular NMR and find clever ways to get rid of the magnetic field. So let's see how this works. For polarization, okay, we use, instead of just the thermal equilibration, we actually use some kind of hyperpolarization techniques, for instance, parahydrogen technique. And by the way, I already said that the Earth field is way too high for us. It's for us, it is really a high field. So we, instead of a magnet, we actually put a very nice magnetic shield. So all stages here are happening in a magnetic field. So what about encoding? Let's as you know, NMR is divided into three big subsets. It's spectroscopy and it's imaging. And in either case, you usually use high field. So for instance, in spectroscopy, you need high field to like pull the lines apart due to chemical shifts. And the bigger the field, the further you can pull those lines apart. At zero field, you have no chemical shift, so you have to rely on something else. And we rely, in this case, on J couplings. And actually, it's a pretty weird situation if you think about it. So at high field, you have a hierarchy of Hamiltonians, right? Various interactions, and if we start from the top, the king of this is the biggest interaction is the Zeeman interaction, and then you go chemical shift, anisotropy, blah 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 blah, and you end up with a tiny, usually poor relative, so to say, J couplings, which are the smallest. And in the zero field regime, this hierarchy is completely upside down. Now zero, now there's J coupling, scalar coupling between the spins is the king, is the biggest interaction, and we actually do apply a tiny magnetic field sometimes as a perturbation. All right, now the third stage is detection. And in high field, you use usually Faraday induction. Okay, and if you let the spins precess, they different types of spins precess at different frequency, and you can read them out like this. And in our case, at zero field NMR, because of this J coupling, different spins are coupled together and act as one entity, so to say. And we don't have different frequencies. We have just the sort of evolution of these multiplets due to J coupling. And by the way, of course, I don't need to tell this audience that thermal polarization is proportional to B, and the efficiency of the signal from the Faraday induction goes to as B, and so basically the scaling of the sensitivity is very close to B squared in high field NMR, and in the case of zero field NMR, it's independent, or we have zero field or very small field, and the sensitivity doesn't depend on magnetic field. So I found that when we started working on this, I had some conceptual difficulties understanding how actually this thing could work, and then later on, when we started doing experiments here, I found that it's kind of hard to explain to physicists how this works, and so my then postdoc Michael Ledbetter and I we wrote an article, so again, semi-popular article explaining how things work in physics today, if you are interested. So these are the three, again, I'm repeating myself, the three stages of NMR, and the clever ways we replace thermal polarization is various kind of hyperpolarization, including DNP, parahydrogen, spin exchange, optical pumping with lasers, and in some cases, my favorite method of actually solving any problem, which is do nothing, okay? So if you do nothing, you still have some polarization. It's called stochastic polarization, because if you just randomly prepare an ensemble of n spins up and down, you will have square root of n excess. And when you have a very small sample, and I'll explain the context where small samples come in then, you know, square root of 1 is equal to 1. So your stochastic polarization is as big as full polarization you can have. And one of the favorite techniques for us is parahydrogen-induced polarization. And I know the chairman and others, some others in the audience are very familiar with this technique introduced by these two gentlemen already quite a few years ago, as you can see. Now, for encoding, we usually use, like I said, chemical shift in spectroscopy, and we use J coupling. And in imaging, we use strong magnetic field gradients. And here we have to play some other tricks. Maybe I have time to mention what we do. And now J coupling. What is the story here? So if you have a molecule and it has two nuclear spins, non-zero nuclear spins, they have magnetic moments, and there is a dipole-dipole interaction between them. Everybody knows about this. And if you write this dipole-dipole interaction, it has this kind of dependence on the relative position between the two spins. And if you go to a gas or a liquid, the molecule tumbles, as they say, and this interaction nicely averages out. And so it was quite a surprise for Erwin Hahn and Charlie Slichter when they quite independently discovered this effect around 1952, and they didn't really understand what was going on because it looked like this kind of a dipole-dipole interaction, except without this angular factor. And so they call this scalar coupling, or because of the letter appearing here, they call it J coupling, which I find is a bit unfortunate because people keep confusing it with JJ coupling in atomic physics and things like this. So the explanation, the modern explanation for this, by the way, historical fact, is that it was given almost immediately after these independent discoveries by Norman Ramsey. He immediately realized and published that we're talking about second order hyperfine interaction. So in simple terms, you have this magnetic field from the nucleus here in a molecule, and hyperfine interaction with electrons perturbs the electronic wave function in the molecule, and the electronic wave function is global for the entire molecule. So this information is carried also to the location of the second spin where the second hyperfine interaction takes place, and this is how these guys can talk to each other. And if you work it out, there is no angular factor this, and voila, we have this scalar coupling. And then again, so remember this program, we are getting rid of magnetic field in each of the stages of NMR, and the final stage here is detection. And for me, it was the reason Alex Pines called me and said, let's do NMR with atomic magnetometers, because an atomic magnetometer is a non-inductive sensor, and then we don't need any magnetic field here. But there are other ways, superconducting devices, and actually now many other types of magnetometers. All right, so this is the idea, but how does this look in practice? And here it is. So first of all, the experiment is happening in a magnetic shield, as I mentioned, and I'm describing here the experiment that was done at Berkeley, and Thomas Theis was one of the guys who did it. I'll show you some other authors as well. And inside, in the middle of the magnetic shield, we have sort of the important component for us is atomic magnetometer. And an atomic magnetometer is a vapor cell, typically with rubidium, sometimes with other alkali atoms or other atoms in general. And what we have here is what's called an all-optical magnetometer. we use one laser beam to optically polarize rubidium atoms in the cell, and another laser beam to analyze the polarization, and it's sensitive to magnetic field. And it turns out that this could be as sensitive as squid. Then we have our NMR tube that comes in from the top, and then we, in this case, we just bubble the parahydrogen in here, and that's that picture again. And this is a pulse sequence. As you can see, it's an extremely simple pulse sequence. You just set this up, then you bubble your parahydrogen. Your reaction occurs here, and some hidden nuclear order is built in your sample, but you cannot see it because there is no preferred direction. So your magnetometer sits here and is waiting to see some field in the z direction. So now I need to confess that I'm actually lying to you a little bit, because this I said there are no magnets, but there is a pulse, and this pulse could be, let's say a small fraction of a Gauss for a millisecond. So it's done with a simple coil. It's a very, very simple pulse. So maybe you forgive me for this. Let's call it a white light. So there's a little bit of a magnet here that just unleashes this internal order built up by the parahydrogen, and then we see this signal on the atomic magnetometer, and the typical size of this signal in the experiments is several picotesla. So it's quite a small signal, but these days reliably detected by atomic magnetometers. And I should say that we used to make these magnetometers and design them specifically for this, but now there are very nice commercial devices that are available from several companies that reach down to 10 femtotesla per root hertz or something like this. Sensitivities are quite enough to measure the picotesla signals from ZULF NMR experiments with very good signal to noise. But what is this parahydrogen magic? And again, apologies for yes.
You said, right, we shall ask. So
Yeah.
what was the detection frequency roughly? And what is the frequency of the FID, order of magnitude?
Yeah. The order of magnitude are J coupling frequencies, and they are typically a few hundred hertz. For some things, they can go maybe up to a kilohertz or something.
Yeah.
The lowest ones are in the hertz range, but typically we detect between 1 and 2 hundred.
Hertz.
You'll
And
see,
I
you'll
mean,
see the
you
signal.
still
Yeah.
have some field presence, right, for quantization. And you know what that field was or is?
We don't need we do not need any field whatsoever because
Sure, you don't need it, but I guess, and that's an experimental apparatus, so there was some field, right? If you would have a non-J coupled sample, what would be the
yeah. So okay, well, indeed. Maybe I should define at this point what we mean by ZULF, by zero. What do we mean by ultra low field NMR? And what we mean is a regime where J coupling dominates other things. Okay, and so this would be the field that will give you, let's say 100 hertz of frequency. Once you are below that, you are in this ZULF regime. Yeah. And so we are talking about I don't know, if you go below tenths of a Gauss or something, you're safely in this regime for most cases. And now what is zero field is now when we do not have any Zeeman splitting of these pure J coupled lines. And typically the relaxation times are several seconds. Yeah, the time scale here is, seconds, 3 seconds. So you don't want your Zeeman splitting to exceed the line width, which is well, sometimes it could be millihertz, so then you really want to shield your field very well, and that is zero field. Also, again, ultra low field is when J coupling is the king, so to say, the biggest interaction, and zero field is when you cannot see the splitting in the line width. So it's all quite well defined numerically, so to say, yeah, quantitatively. So in that sense, anything, any field smaller that doesn't split the J coupled lines by more than a line is a zero field. So no problem.
Okay, so if it's below the line width, and what line width do you typically have?
Yeah, so it depends. It depends. So it could go down to millihertz.
Millihertz.
Yeah. I'll show you some examples.
So the Lama frequency would be millihertz if there
Yeah,
was one.
yeah, that's
And I
right.
guess you see splittings left and right of zero, but they're not exactly symmetrical. They're just a little bit.
Yeah, we see. Let me show you some signals, and then we'll go from there. But let me just keep my sequence so I don't lose the train. So this is what was used in this experiment by Thomas Theis et al. So we had a styrene molecules, and hydrogenation occurs across a double bond, and this is now a parahydrogen. And for hydrogenation, there is a catalyst here that's used, and now you have this parahydrogen, two atoms attached in different locations in the molecule, and this happens quickly on the spin physics scale. So it's still a parahydrogen, but now the parahydrogen is not an eigenstate, so it's not, now you have to think about the eigenstates in this larger spin system, and that what allows you, parahydrogen is spin zero, and it's NMR insensitive, but after the reaction, this is expanded into something that becomes NMR sensitive. And in this case, you take the spectrum. This is, by the way, the spectrum taken from that paper. Okay, and so what you see here is actually something around 100 hertz. That's the J. That's the HC J coupling in this case. There is 3/2 J and 2J, and this is exactly as we expect from theory. And this interesting color coding that you see here, it comes from different parts of the molecule. So let's start with this blue one, which is this. And here you have CH3 system, and theory, there's a very simple theory for this, tells you that you should have J and 2J lines, and let's have J and 2J. And indeed, we have that. And you see that these lines are relatively narrow, and they are narrow because the ring is far away. This is fairly isolated, and so these lines are more or less unperturbed. The next one is CH2 system that is here, and now it is closer to the ring, and so all these lines are, there's much more perturbation, and then the red one is these carbons. And you might say, I don't remember if I have that. I don't think I have the theory. You might say that all of this is some kind of a big collection of garbage, but if you run, let's say, a spinach simulation of this, all the minute details are reproduced. This is really amazing. So this is not garbage. This is like some of my colleagues like to say, it's a spectrum rich in information. So about what is going on here. And let's see. So this was then really the NMR without magnets, except for this start pulse. And we needed to have a graphical abstract or whatever it's called for this. And And somebody came up with this, and I love this picture because you look at this first, you think you're looking at some kind of a modern painting or something like this, abstract painting, but it's not abstract. It's everything here is meaningful. So here's your atomic magnetometer and pump and probe beams. Here's your molecule and the para-hydrogen attaching, and then the polarization distributing over the molecule. And this is even your spectrum with J and 2J lines. So this is basically the recap of the story of what is zero field NMR. And like I said, if you apply a little bit of magnetic field, then you can split the lines, and this is very useful for diagnostics, for actually determining which kind of multiplet you have. But now I want to ask a question. So you can do, I hope I have convinced you that you can indeed do zero field NMR, but why would you want to? What is the reason? And I'll try to answer that. So first of all, the apparatus for this turns out to be, well, maybe inexpensive. Is it depends on how rich you are, I guess. It's still something that is not not change, right? So I would say that you can build a decent homemade ZULF NMR apparatus for 30,000 euros or something like this currently. But it's relatively inexpensive compared to high field NMR, and it's portable. So you can put it on a cart, and I see no reason why you cannot further compress it with investment in engineering into a cell phone or something like this. And in fact, some people are working in that direction, like making various aspects of this small and compact and extremely cheap, like Michael Tyler in Barcelona, for example, is interested in this kind of work. On a scientific side, in the presence of a high field, various couplings are truncated, and here in the zero field, you have direct access to all kinds of things like, for instance, tensor components of the J coupling tensor, which is very interesting and not very well explored yet. On a practical side, because you are dealing with frequencies of only hundreds of hertz, there is no problem with skin depths, and you can make your NMR tubes out of metal. How's that? So we did experiments where NMR tubes were made out of metal. No problem. It's important, for example, for the study of chemical dynamics and catalytic converters and things like this. One of the problems in high field NMR is that you're very sensitive to inhomogeneities in the sample because of the susceptibility gradients that broadens your line, And here we have zero field, so we don't care. We can do measurements with any kind of inhomogeneity. So one can prepare and use quite different long-lived spin states. For example, at zero field, there is such a thing as heteronuclear spin singlets. Okay, so for example, carbon hydrogen spin singlet state, and they also live long generally, and there are special hyperpolarization modalities to produce such states. So it's an interesting and useful feature here. And generally, when you go to lower fields, you have enhanced relaxation rate contrast, and then we can take advantage of this. An important point I'd like to make is one, at least I think Alex Pines always emphasizes this, and I think it's a very, very good point that one cannot even ever think that zero field NMR will be in direct competition with a beautiful and well advanced high field NMR. However, it could be useful in a number of niche applications, and that's how one can think about it. Sort of, it's a complement rather than competition to high field NMR. And I already said that we have no thermal polarization at zero field, so for us, hyperpolarization is necessity and not luxury. And this gives me a very good excuse to advertise. Maybe you already know, there's a relatively recent paper. There was a project that was spearheaded by my colleague Igor Kaptug, and who assembled this very nice team of experts familiar with different types of hyperpolarization. And this is like a comprehensive, relatively modern survey of hyperpolarization techniques. Now, I would like to present to you sort of the general overview here. And let me ask the chairman, actually, when do you want me to stop? We started at 6 more or less, and now it's 6:37. So I have an idea of what to do
Sure.
approximately.
We usually stop after the questions around 7-ish.
All right.
So if you want to have 10 to 15 minutes discussion, yeah, you can still talk like for 10 minutes, 15 minutes.
Perfect, perfect. And by the way, since we already stopped for a second, are there maybe some questions, some burning questions, or even not burning?
Anyone from the audience, take the opportunity. This is not YouTube, this is live.
Yeah, this is a proof. It's like yeah. I can hold also today's newspaper or something like that.
Looks like everything was clear so far.
All right. Either that or everybody's asleep. It's one of the two. Okay. Anyway, this is a map of the status of the field, and I guess I would like to start here with hyperpolarization. And so on in this diagram, with I color with green color is something that has already been done, and with black color what's in process, so to say. When we come to hyperpolarization, so I must say, you know, we want to get away from thermal polarization, but there is a big advantage of this because it's highly universal. So for example, for parahydrogen polarization, you need certain kinds of molecules, and you stick any molecule in a magnet, and it gets polarized. So actually, a lot of our work is done by having a magnetic shield and placing a Halbach array with a field of 1 to 2 Tesla. It doesn't have to be a homogeneous field, and then we put a sample in this magnet for a few seconds. Then we either drop, or with a belt setup that moves the sample up and down, we shuttle it up or down, either way. So we do a lot of work with this. Parahydrogen has really developed a lot, and in order to broaden the scope of molecules that you can polarize, various modification like FIP with a spin exchange, or also Saber. It's polarization and reversible exchange, where you don't actually change the molecule, and then you can still have chemical exchange for polarization of further compounds. we can use spin exchange optical pumping. A lot of stuff can be done with classical DNP, and a very interesting recent direction in ZULF is application of photo kidnip. It works very well, and it works differently at zero field. And one thing that we are working towards but haven't achieved yet is to detect zero field NMR using single spin sensors, the single color sensors in diamond. And then we will be sensitive to very small samples, ideally one molecule, and then we will, of course, rely on stochastic polarization, but this is still in progress. So this is what's happening on the hyperpolarization front. Now, around this, there are various techniques that are being also explored to extend the basic experiment here, basic ZULF NMR experiment. For instance, there is polarization transfer. I'll give you an example in a minute. Relaxometry, partially aligned or oriented molecules to bring back the formerly averaged dipole-dipole interactions. 2D NMR techniques, for instance, where one dimension is ZULF and another is high field. This is powerful. And then single molecule ZULF, and another very interesting direction that's being pursued at the moment is detection of zero field NMR by detecting the radioactive products of the molecule of the nuclei that participate in a zero field NMR. This is beta and gamma NMR, and we are working on this in collaboration with CERN at the moment. All right, on the detection side, okay, you can still, if you like, shuttle your sample back into high field and detect inductively. We very rarely do it, but sometimes we do it for comparison, especially with benchtop NMR systems from Magritech. We have several of them in the lab. SQUID, optically pumped magnetometer, and recently we've been doing some work on detection with anisotropic magnetoresistance, and this is an all-solid state platform. It's maybe not as sensitive as these guys, but could be cheaper and may have certain advantages. Diamond has already been used to detect high field NMR, but now we're working to extend it to zero field NMR and like I said, beta and gamma rays. And for we've been studying, and others, there are several groups working in this field at the moment, biomolecules, quadrupolar nuclei, catalysis, including in metal container, chemical dynamics, fundamental physics. I'll say a few words about this. There is ongoing work on quantum control, and soon to be some work on chirality studies at zero field. Yeah, so things are getting somewhat example of work from a couple of years ago, and the goal of this work is creation of very pure hyperpolarized fumarate free of any residual contamination from the catalysts or solvents. And here you have a precursor. There is a hydrogenation with parahydrogen that is happening here, and then there is a magnetic cycle that transfers the polarization that is initially created in hydrogens into carbon 13, and then it's all followed by purification, just to give you an idea of the level of present sophistication of this. And the application of fumarate, of course, is biology and medicine. So when you attach the parahydrogen, you change the molecule. But several years ago, Simon Duckett and coworkers invented this technique called spin amplification by reversible exchange. And the idea here, I guess I don't have that slide, but we can see here, is that you have some kind of a catalyst, here, and so you have parahydrogen, which polarizes this molecule in a reversible way, and then the molecule you want to polarize docks to this mothership, get polarized on docks, and then it comes out polarized, and then you can have chemical exchange to further polarize other things. And so this is a master student now a PhD student in our group, Eric van Dijk, and here's also a relatively recent paper where this technique was used to obtain zero field J spectra of C13 methanol and ethanol in both isotopically enriched and natural abundance samples. And of particular interest to us was ethanol extracted from a store-bought sample of vodka, with a sample disappearing mysteriously after the experiments. Yeah. Yeah, so I already mentioned that photo-induced, chemically induced dynamic polarization is something that can be used in various combinations. So you can do high field kidney detected and zero field, and it turns out that you can also do low and even zero field hyperpolarization, and you create different states while you do this. And the first object that has been used so far is this rather common for the kidney model system of this tetraphenylporphyrin. I'm a physicist. Sorry, I have difficulty pronouncing long chemical names, and the benzoquinone. Yes, so it's also a collaboration now between Mainz and Barcelona. And if you're interested, there is a recent paper on this topic. Another collaboration that we are pursuing is with Sami Jinan, who is a great expert on the classical dynamical nuclear polarization. And you might say, isn't this crazy? That this has, here's 7 Teslas. You use high field, and then you do zero field detection, and you might say, maybe it's initially crazy, but if you think about it for a little bit, and we did, and we wrote it up recently, actually, there is a lot of practical reasons for combining classic DNP and detection with ZULF. And one of them is that you can find DNP these days already in hospitals, and there are many applications where this combination can be particularly powerful, both for spectroscopy and imaging. So let me see the time. We need to leave some minutes for discussion. So maybe I will just flash through the remaining slides without details. It turns out that the ZULF NMR is also very good, and in many ways unique for studying certain problems in fundamental physics. And here is one example. Let me show you a really nutty Hamiltonian, a really crazy Hamiltonian. Here you have nuclear spin, and here you have, you know what? The acceleration of gravity is spin times the acceleration of gravity. So you can write this, and it will be violating everything: parity, time reversal invariance, equivalence principle. Nevertheless, there are exotic theories of gravity that predict that such an interaction should occur, such spin-gravity coupling should occur. And therefore, it is important to keep those crazy theories at bay, to do an experiment and either discover this or tell them, no, it's a very small effect. And these experiments are indeed ongoing, and in particular, We have a collaboration with a group at the Jagiellonian University led by Professor Shimon Pustelny, where we're doing this very experiment. And the idea is that you compare NMR frequency with magnetic field along and opposite to the gravitational field. And it turns out that it's actually impossible to do this with regular NMR because you will never be able to separate the fluctuations in the magnetic field present in the laboratory with the real effect you're looking for. But what we use here is a comparison of effect on two different multiplets. And if you work the mathematics out here, you can see that the magnetic field and the exotic interactions have different dependencies on the frequency of different multiplets. And this is a key idea, which you can say intramolecular comagnetometry, if you want, that allows us to extract the useful effect. We can also use, let me skip this, zero field to search for dark matter, and we've done some experiments about it. But I must say the status of dark matter searches for today is that there are other techniques that also are developed with our own participation here that are doing a bit better or a lot better than ZULF NMR. Fundamental physics is not only tabletop, it's also accelerator physics. And actually, there was a proposal that we formulated some years ago on using ZULF NMR to make polarized targets with some advantages that you can have very fast switching, which is good for systematics, for accelerators, etc. And this paper was read, and then forgotten. But I'm super delighted that just now there is new activity, and actually right here in Mainz using the accelerator here. And this is Simon Duckett group, and we're helping them a bit with this experiment as well. So it's very exciting for me. Yes, for fundamental physics, you need hyperpolarization as well, but the task is maybe somewhat different from what, say, biologists need. Biologists typically have some small amount of molecules that's hard to see with thermal polarization. Then they hyperpolarize them, then they see them. Well, for us, this is insufficient, and we really need, there are some requirements here. I'm not going to go into them, but we need really a lot of hyperpolarized spins. So our requirements are somewhat different, and it's important to improve on that front, and there is some work that is ongoing in this direction. Now I'm at the end, and I want to say that our lab at Mainz really draws its energy from collaboration with many people all over the world. This is, for example, Professor Magdalena Kowalska at CERN, and some of the folks that I already mentioned. And these guys here are alumni, and I want to mention John Blanchard, who came here after graduate school at Berkeley and helped me put this lab together. And then the next generation of postdocs like James Eels and Kirill Sheberstov and a bunch of PhD students. And our lab is now spearheaded by very talented young man, Danila Barsky. And this is a really dream team to have. And this year, we are extremely happy to host Alexei Yershov from New York University as a Humboldt professor with us. And if you are interested in a light review of the topic, I invite you to check out this lower than low paper from a couple of years ago. And And at the moment, with a group of co-authors, we are completing a really long and detailed review of the field. Hope to offer it to you shortly. And now this is the plan that I had, and I believe that more or less I have been able to fulfill this. So we stop here. Thank you.
All right, Dmitry, only you of everybody else, thank you so much. Great presentation, very educational, but very interesting as well.
Thanks.
Do we have any questions from the audience before I start my large list of questions here? So there's a question. Andreas Berg is asking, what mechanisms and motions, correlation time, are responsible for relaxation time, ZULF, for line width, and T1, no microphone? I'll reread. What mechanisms and
Yes.
motions, correlation time, are responsible for relaxation time, ZULF, for line width and T1?
Yeah, it's a very good question. I think the theory of this is nascent, so to say. I know that Alexei Yershov actually is working on seeing where the traditional Redfield, whatever, relaxation theory works and where it fails. And what we find in some cases is that it seems like the classical relaxation theories, work even when their applicability range is not when they're not supposed to work. And you can see that the relaxation times that we have are typically a few seconds, so are very similar to what you have in higher fields. So I don't know if I can say too much more about this. Certainly, dipole interactions play. They average out. For on average, but they play a role in the relaxation.
Yeah, we still have all the collisions of the molecules, right?
Absolutely, yes, of course.
Any other question from the audience? So you mentioned quite a few interesting things. I could ask about chirality, niche applications, single spin NMR, or if force detected NMR is still a topic, but maybe I'll start with, you said DMP and ZULF is a great combination. Why?
Yes. So like I said, DNP machines are available
Sure.
in hospitals, and but for example, you can imagine having experiments at the bedside of a patient where in the hospital where there's the DNP machine and there is no um, spectrometer available. So that can be one application. To give you an example, there was, yes, this paper. Another thing is that we can do imaging in different ways as well. We can do there are ideas so-called molecular imaging, so imaging of different types of molecules, which is different from when you have a sort of the regular MRI with location of protons, for example, and things like this. So yeah, in the end, we are quite excited about this, and in fact, have an ongoing collaborative project with Sami. We are building a new zero field machine to send there, and so you'll see results coming out very soon.
I mean, do you actually care how the samples are polarized?
No, we don't necessarily care how they are polarized, but we care that they are polarized, right? And DNP is one of the most universal systems for polarizing a very broad range of molecules. And by the way, SAMI reported some very interesting developments at the recent hyperpolarization conference in Leipzig that open very exciting possibilities for creating these buckets of polarized spins, and that's another thing we're trying to put together at the moment.
Okay. Again, the question to the audience, anyone, anything. What do you want to do with chirality and ZULF?
With chirality, we there is a proposal by John Blanchard, yeah, my former postdoc, and Jonathan King, that says that by measuring off diagonal J couplings, you can have a direct measurement of chirality just in the ZULF experiment, and that's something that we also would like to set up and measure. Also, our colleagues in China are working on that at the moment.
In Hefei?
In Hefei, yeah.
Yeah, nice. All right. If there's no further questions, let's please thank our speaker again. That was very nice. Thank you, Dmitry.
Thank you so much. Enjoyed it.
It was great having you. It was great having all of you attending. Thanks so much and have a good evening.
Thank you. Bye-bye.